everyone. I'm actually going to screencast this lesson in advance just because I'm worried that I might be out sick. So just in case, I thought I'd go ahead and do the screencast in case you were left with us up tomorrow. So we are starting Chapter 5. Chapter 5, the main topic is integrals. And today we're doing Section 5.1a, which is using rectangles to calculate area. So the question that we're going to answer over the next couple of days is, how do we calculate area that is bounded by some funky curve? So we know how to find areas of rectangles and circles and trapezoids. How do we find an area of a space that isn't a straightforward geometrical shape? So for example, the area that is under this curve and above the x-axis between two values of x. So this area, how do we find it? So there is a way to find the exact area, but before we learn the way, which is using integrals, but before we learn that method, we're going to learn how to approximate the area by breaking the region up into rectangles. So if we split the region up into rectangles, whatever the heights are, and we could have one over there, then we get an approximation for the area. Now there are different types of rectangles, and the type that we use changes how the approximation is calculated, but for the most part, all of these are just approximations. So let's take a look at the different types. So there are basically 5 different types of rectangles that you can use. So the first type is called upper or circumscribed rectangles. And what happens is, if you look at the sides, so say this is your beginning and ending x value and you decided to break it into 4 rectangles, well, each rectangle has 2 sides. If you want an upper estimate for your area, you would always pick the side that's higher to determine the height of your rectangle. So again, this rectangle has a side here and a side here. The side that's higher is this one, so that determines the height of the rectangle. But this rectangle has a side here and a side here, so this side is higher, and then same thing, this side is higher. So we end up with these 4 rectangles, 1, 2, 3, 4, and we would add their areas together. And obviously our sum, if we were to do this, our approximation would be higher than the actual value of the area under the curve. This next one would be lower or inscribed rectangles. And again, you just look at the 2 sides of the rectangle, and whichever one is lower, that determines the height of your rectangle. The next 2, these next 3 actually, these guys are the most common types on the AP exam. The College Board will always ask you either left, right, or midpoint. Your book also most commonly asks you for left, right, or midpoint, which is nice. So left-handed rectangles, if you look at the 2 sides of the rectangle, the one on the left determines the height of the rectangle. Doesn't matter if it's higher or lower, the one, when you look at the 2 sides of your rectangle, so 1, 2, the one on the left determines the height of the rectangle. Side here, the one on the left is the height of your rectangle. Right-handed rectangles are always determined by the height on the right. So whatever, if those are your 2 sides, the one on the right determines the height of the rectangle. Right, right, right. And those are your 4 rectangles. Midpoint rectangles are determined by the height in the middle. So you have this side and this side go halfway in between, and whatever the height is halfway in between, that's your height of your rectangle. So here you have this side and this side, go halfway in between, find the height, that's the height of your rectangle. Same thing here, same thing here. Okay, so those are the different types of rectangles that we can have, and now I'm going to show you how we use those to calculate area. So for our first example, we're going to find the area under the graph of y equals x squared from x equals 0 to x equals 1. Now, I have a great method that I use for all of these problems, but this first little part of the example, we're just doing it using one right-handed rectangle. So if we approximate this area using one right-handed rectangle, so we're going from 0 to 1, the side that's on the right is this guy, so this is the height of our rectangle, and that's our rectangle. So the area of this rectangle would be our approximation for the area under this curve that we're calling S. So your book has a shorthand. The College Board, this is not standard shorthand, this is just your book, but you do need to get to know it because they use it in your homework. So when you're using one right-handed rectangle, they call it R sub 1. So our R sub 1, the area of this one right-handed rectangle, the area is width times height. The width is the difference between the two x values, so the width would be 1 minus 0. And then the height would be whatever this y value is, and the height here is 1. So our R sub 1, or our approximation of this area using one right-handed rectangle, would be 1. All right. Then do the same thing using 4 right-handed rectangles. So if we split this into 4 rectangles, and we're going to do right-handed, so we're going to have heights that look like this. Right-handed rectangles, 4 right-handed rectangles. So we need two things. We need a width, and then we need the heights. So the way that I like to do these problems, and I'm going to show you why this is going to work so well for you, is especially if you have to do multiple approximations, is I like to make a table. It seems kind of weird, but it actually, in the long run, will save you time. If this is your x and this is your y. All right, so we need to find these x values. So it would help if we knew how to find the width. So in this case, we're going from 0 to 1. We have 4 rectangles. We know the width is 1/4. Just in general, width is always b minus a over n, where this is your right endpoint. This is your left endpoint. And this is the number of rectangles. So in this one, our width would be 1 minus 0 over 4, or 1/4. All right, so our x values, I'm going to erase some of this just so I have space. All right, so our x values, we start at 0, we're walking by fourths. So we have 1/4, 2/4, which is a half, 3/4, and then 1, which is 4/4, so we end at 1. All right, so if we plug in our x values, so we have, I'm going to go ahead and list every x value I see. 1/4, 1/2, 3/4, and 1. And then I find all my y values. So everything's squared. So 0, 1/16, 1/4, 9/16, and 1. Every rectangle has 2 sides. So think of a rectangle, like if we had 4 rectangles, each rectangle will have 2 x values, one on the left and one on the right. So our area, I'm going to write area, which is approximately equal to r sub 4. All right, remember area of a rectangle is width times height, so 1/4 times the first height. So you look at the first 2 x values and you pick the one on the right. So this is going to be your height. So 1/16 plus 1/4 times. Now you look at the next 2 x values. Be careful because you use every x value twice. So the next 2 x values would be this one and this one. So you're going to pick the y value. So you pick the y value on the right. So now our height is 1/4 plus 1/4 times. Look at the next 2 y values, here and here. Pick the one on the right. And then the last y value here and here, you pick the one on the right. All right. One of the other things that you're going to get used to as you work these problems is if all of your rectangles have the same width, then you can just write the width once, factor it out. I'm going to, just for space, I'm going to go up here and say that this is the same as 1/4 times 1/16 plus 1/4 plus 9/16 plus 1. All right, so that's our R sub 4. If you want to actually simplify it, you get 1/16 plus 1/4 plus 9/16 plus 1. All right, so you end up with an exact area of 15 over 32. All right, so a little less than a half. All right, so our R sub 1 was 1. Our R sub 4 was 15 over 32. First question, are these approximations greater or less than the actual area? These approximations would be greater. Which one is better? The R sub 4 is better because there's a lot less space that is included that we shouldn't be including. So there's less extra space. We just have these little tops here included instead of this whole big thing. All right, we're going to do the same thing using 4 left-handed rectangles. Now the nice thing about having a table, and remember when you make your table, don't think left or right. Include every single x value you see, including the 0, even though we didn't use it, because we're going to use it now. We're going to find L sub 4. So we already have our table, so we're going to use the y values on the left now. So for our first pair, all right, so for our first pair, so we have 1/4 out front, pick the y value on the left. Next pair, pick the y value on the left. Next pair, pick the y value on the left. Last pair, pick the y value on the left. So our left-handed approximation, which is 1/4 times this nice little quantity. Now let's figure this out. So our left-handed approximation is 7 over 32. All right, is this greater or less than the actual area? This would be less. So you'd have all of your rectangles for the lefties would look like this, and they'd all be below the actual area. So what would be a decent approximation? Well, one really good approximation would be if you took the left and the right and averaged them, right? And you get a pretty decent approximation. But just know that the left nor the right, neither of them is great by themselves. One's going to be over and one's going to be under. I'm going to put a little note here, just so you know, for over versus under. Approximation. All right, so an over versus an under approximation, it has to do with the direction of the function. So if you have an increase, so if your function is increasing, then your right would be an over and your left would be an under approximation. If your function is decreasing, it's going to be the opposite. Your right's going to be an under and your left is going to be an over. Personally, I have never memorized this. So what I do is, if on the AP exam, if you have to justify why is your approximation an over or an under approximation. So if for this one we have say we do the right-handed sum with the increasing function. If I don't remember, I just draw an increasing function, pick a spot and do a right-handed rectangle and think, oh my goodness, I'm over. So then my answer would be, this is an over approximation because we are using right-handed rectangles on an increasing function. So the main thing that determines if it's over or under is the function increasing or decreasing, and are you using right or left-handed rectangles? So increasing or decreasing. I usually say rectangles go with direction. Rectangles go with direction. All right, how could we improve our approximations? So I'm going to see if I might skip this. I'm going to pause and get to your book. Okay, so what we have here is we have that same graph, still from 0 to 1. So if we were to use right-handed rectangles, one rectangle would give us this area. But if we were to increase the number of rectangles, say, to 20, right? There's our 4. Let's see, that's 5. I can't get it to 4. It's too hard. But anyway, so there's 5. That's kind of close to what we found. So if you notice down here, they're showing the actual areas a third. We got 0.44 with 5 rectangles. If we go to 20 rectangles, we're getting closer. If we go to 40, we're getting a lot closer. As we increase the number of rectangles, we get closer and closer and closer to the actual area. I'm hoping that you can see where this is going, because eventually we are going to take the limit as the number of rectangles approaches, you guessed it, infinity. But for today, we're not going to do that. And I'm not going to make you add 200 rectangles together. With 200 rectangles, we're correct to just 2 decimal places. So it takes a lot of rectangles to get the exact area, which is why we use the limits, and we do the limit as x approaches infinity, or as the number of rectangles approaches infinity. Same thing with lefties. If we were to do left-handed rectangles, we'd start with an area of 0. Notice all of our approximations now are under approximations, and we get closer and closer to the area, but we always stay under. So again, with 200 rectangles, we're still only correct to 2 decimal places. All right. Okay, back to notes. All right, so we're going to do this one. Approximate the area under the curve y equals x cubed minus 3x plus 5 from 0 to 3 using 3 right, 3 left, 3 upper, 3 lower, and 3 midpoint. So the first thing that you want to do is make your table. Let's first find our width. So our width, so this is our A, this is our B. So it's B minus A, 3 minus 0, over the number of rectangles, which is 3. So our width is going to be 1 for every single one of these. So you're welcome. All right, so now let's make a table. All right, so we have an x, we have a y. We're starting at 0, and then you just add widths. You walk by widths until you hit the other endpoint. 1, 2, 3. All right, now you plug into your function. So f of 0 is 5. So at 1, we have 6 minus 3, so 3. At 2, let's see, we have 8 minus 6 is 2 plus 5 is 7. And at 3, we have 27 minus 9 is 18 plus 5. We're at 23. So there's our y values. Once you have your table, these should be really quick. As a matter of fact, I'd really like you to pause and see if you can find at A, B, C, and D, not E. So leave E for later. But do A, B, C, and D. Just try and figure out all those answers. So 3 right, we'd write R sub 3. All right, so we have our width times the 3 heights. So if you think of these as your 3 rectangles. So when you're doing righties, you pick the height on the right. So 3 plus 7 plus 23. So our R sub 3 would be 33. If we do an L sub 3, width is still 1, and you pick the 3 left-hand heights. So you have 5 plus 3 plus 7, which is 15. If we do 3 uppers, so if we do 3 upper rectangles, what you do is you look at each y value and pick the bigger one. So the width is still 1. Between 5 and 3, you pick 5. Between 3 and 7, you pick 7. And between 7 and 23, you pick 23. So you end up with 35 is your upper sum. And then lower, let's call it low, so 3. So between 5 and 3, you pick the lower one, which would be 3. Between 3 and 7, the lower is still 3. And between 7 and 23, the lower is 7. So your lower sum would be 13. Midpoints are a whole different ballgame. So when you do 3 midpoint rectangles, you have to make a whole new table. So the reason you have to make a new table for midpoint is you have to find the y values at the midpoint of each of these intervals. So the midpoint between 0 and 1, so you need to find the function at a half. The midpoint between 1 and 2 is 3 halves, and the midpoint between 2 and 3 would be 5 halves. It's not the average of the y's. You average the x's and then plug them into your function. So if we were to find these y values, let's see here. So we have x cubed minus 3x plus 5 evaluated at x equals 1. Okay. So the first one is 29/8. Then at 3 halves, you get 31/8. And then at 5 halves, you get 103/8 or 105/8. I think that's 105/8. Forgive me if I'm wrong. I don't have my glasses on. All right. So there's your 3 y values. So your part E, which I'm going to go ahead and put right here, your part E, which is your midpoint, the width is still 1. The width isn't a half. The width is 1. It's the difference between each of these guys, right? So, yeah. Okay, or sorry, the difference between each of these guys. Pointing to the wrong things. All right. Okay, so anyway, so it's really just your 3 y values at your 3 midpoints. So you have 29/8 plus 31/8 plus 105/8, and your answer is this plus this, which is, I think, 165/8. All right, so in case you're wondering, 165/8 is around 20.625. So this is around 20.625. Midpoints, if you had to choose between left, right, upper, or lower, midpoints actually give you the most accurate of those 5 approximations. So there you go. All right, so 2003, number 3. I'm going to put this up here. Let's see. Here it comes. Okay. So 2003. Okay. Oh, this is such a great problem. Make it a tiny bit bigger here. All right, so the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable, strictly increasing function r of time t. The graph of r and the table of selected values from 0 to 90 minutes are shown above. From the data in the table, use the data in the table to find an approximation for r prime. Show the computations that lead to your answer and include units. So I don't know if you remember this or not from chapter 2, when, and I think also chapter 3, when you have to approximate a derivative from a table. Remember, this is your input, this is your input, this is your output. You can think of it as turned sideways. 45 falls right in here. So remember, you go up one, down one, and do slope of the secant. So our r prime of 45 would be approximately equal to, so change in y over change in x. And make sure you write it as a difference quotient. You don't even have to simplify. I'm going to go ahead and at least do the differences. So you get 15 tenths or 3/2. Your units are the units of r over the units of t. So it'd be gallons per minute, or gallons per minute squared. All right, the rate of fuel consumption is increasing the fastest at time t equals 45 minutes. What is the value of r double prime? Explain your reasoning. Again, take a minute, see if you can figure this out, and then come back and watch the video. So r double prime of 45, if the fuel consumption is increasing fastest, that means that the rate has a max at t equals 45. So if r prime has a maximum at t equals 45, that means that r double prime has to be 0. R prime as a it would actually be an absolute max. I'm just going to say a max. At t equals 45. All right, approximate the value of the integral from 0 to 90 using a left Riemann sum with the 5 subintervals indicated by the data in the table. Is this approximation less than the value of the actual area? Explain your reasoning. So let's take a look. I'm going to go ahead and do this up here. The nice thing is they've already given us a table. So the integral, let's see if I can squish this, from 0 to 90 of r of t, dt equals. So we have subintervals, but these widths, these rectangles, are not equal width. Each rectangle has a different width, so you have to find all of your areas separately. So the first width would be from 0 to 30, and so it would be 30. Remember, these are left rectangles, so if you can think of this as turned sideways, right? So you'd have 0, 30, 40, 50, so forth, right? Your height's 20, 30, 40, 55, so forth. So our left height, if we're going from 0 to 30, the height on the left would be 20. The next width, we're going from 30 to 40, so the width is 10, and the height on the left is 30. The next width from 40 to 50 is 10, and the height on the left would be 40. The next width from 50 to 70 would be 20, and the height would be 55. And the last width from 70 to 90 would be 20, and the height would be 65. All right, then you'd have to, you can actually leave it just like that. If you have a calculator, you could compute it, but if you don't, there's no reason to compute. There's really no reason even if you have a calculator. All right, is this approximation less than the actual value? Explain your reasoning. All right, we're using left-handed rectangles. This is a left Riemann sum. So when you're using left-handed rectangles on an increasing function, they're all going to be below the graph. So your answer to this part, this second part, I'm going to put it down here. Your answer would be yes the approx is less than the actual value, oops, dt, because we are using left rectangles on an increasing function. All right, and we don't have to do part D because you haven't learned enough to be able to do part D. Okay, so I have an intro to tomorrow's lesson. I mentioned this in one of the classes today, sigma notation. So a quick review on sigma notation, just so you've got it, and then we can just jump in tomorrow. So there's a letter down here. This is called the index. This is the lower bound. It's like your starting value that you plug in. This is your upper bound. This is your ending value that you plug in.
Chloe Graham, please come to the Student Center South. Chloe Graham, please come to the Student Center South.
And what you do is you start with this lower bound, you plug it into your function, right? So you get that guy, and then you add. Sigma means sum, so you always add. Then you walk by integers. So the next integer would be 2. You plug in a 2, right? And then you add. Then you plug in a 3. You add. You plug in a 4. And then you stop because 4 is your upper bound. You add all those together, and this value is the value of your sum. So, if we had to write this in sigma notation, first thing you do, write a sigma, pick a letter for your index. Then you write, what's easiest is to write whatever is staying the same, and then look for what's changing. Whatever is changing, that's your I. What is the first I that's plugged in? 3. What is the last I that's plugged in? 9. So for this guy, it looks complicated. It's really not. 4 over n is the same in every single term. You have a 5 plus 4 over n cubed in every single term. The only thing that's changing is we went from nothing to n. Technically, it's not nothing, it's a 1, because it's 4 times 1, and it switches to 4 times n. So that's where our I goes. The first I is 1, the last I is n. All right, the last thing that I want you to do is copy these into your notebooks. Just copy them, have them, keep them, and we will use these tomorrow. So write down these formulas, pause the video if you need to, and that's it for the day. I am skipping this. We'll do this later. So that's it. Rectangles and then just the beginnings of sigma notation. I hope you guys have a good day. Hopefully I'll be here tomorrow and this won't matter. Thanks. Bye.